Hello everybody, in this video I'm going to discuss the different maximum super elevation rates recommended in Green Book for designing highways and streets. Let's start our discussion with a simple example. Suppose we're to determine the required super elevation rate for a 60 mile per hour curve with a radius of 1,330 feet. As an option, we can look it up in Table 3-8, Green Book 7th edition, which is for maximum super elevation rate of 6%. Well, it says for a 60 mile per hour curve with a radius of 1,330 feet, the required super elevation rate is 6%. Instead, we can also refer to Table 3-12, which is for maximum super elevation rate of 12%. Well, here is the design speed, 60 mile per hour, and the radius value is in between these two, so the required super elevation rate will be almost 10.9%, more than 1.5 times and nearly 2 times the required one obtained from Table 3-8. Now one may ask two questions. First, given the same design speed and radius, how come it comes to two values that different? And second, if referring to different tables comes to different required super elevation, which table we should use for a specific road? I'll try to explain it in this video. It's actually all about the proportion of which the side friction contribute to sustaining lateral acceleration. Let's go about the example we started with in another way. Well, the design speed was 60 miles per hour, maximum side friction factor corresponding to this speed is 0.12. If you remember, we considered two different maximum super elevation rate of 6 and 12% for the given speed and related maximum side friction using this simplified equation, which I believe we're all familiar with. We can calculate the minimum radius for each Emax. Now let's solve the equation for the sum of E and F and put the given speed and radius in the equation. Doing this, it says for a 60 mile per hour curve with a radius of 1,330 feet, the sum of E and F has to be at least 0.18. Now, if the F value is known, we can simply subtract it from 0.18 and get the required super elevation rate. But this is where it actually gets a little complex. As long as the radius is around about minimum radius, F value is around about F max. But the larger it gets compared to minimum radius, the smaller F value we're allowed to use. Since the given radius equals minimum radius for Emax of 6%, we can put F max for F in the equation and subtracting it from 0.18, we get 6% for required super elevation, which is in agreement with what we get from Table 3-8. But it's not that easy for Emax of 12% because the given radius is larger than minimum radius calculated using Emax of 12%. Well, we're not going to go through theoretical procedure of side friction distribution. What we're seeking is to understand the differences between tables for different Emax. So let's put the required super elevation we obtained from table 3-12, which was for Emax of 12%, in the equation and this time solve it for F value. From table 3-12, for a 60 mile per hour curve with a radius of 1,330 feet, the required super elevation was 10.9%, let's say 11%. Subtracting it from 0.18, we get 700 for F value. It means almost only 60% of maximum side friction is considered to contribute in sustaining lateral acceleration, which leads to requiring a more super elevation rate. Now, what happens to the rest? The 40% The answer is it's kept in reserve. So far, we can say we've come to this point that for a given radius and speed, the higher Emax we select, the lesser proportion of maximum side friction will be counted on to sustain lateral acceleration. So a higher superelevation rate will be required and higher amount of side friction is kept in reserve. But by selecting smaller Emax, higher proportion of maximum side friction is considered to be sustaining lateral acceleration, so lesser amount of side friction is kept in reserve and lesser superelevation rate is required. This is the answer to the first question on differences between different tables of Emax. But what's the reason behind this different distribution of E and F? First, some drivers tend to travel faster than design speed and flatter curves, especially in rural areas. This is the reason why lesser side friction is considered in designing curves with a radius flatter than minimum radius, and why some portion of side friction must be kept in reserve as a safety margin. As we found out, the higher Emax we select, the wider this safety margin gets, which makes it more appropriate for rural areas where the running speed is higher than urban areas. Second, rough terrain makes trucks lose more speed than passenger cars, which causes different level of demand for sustaining lateral acceleration. Using too high superelevation rates, slow drivers will experience too much negative side friction, which can result in excessive steering effort and erratic operation. Congestion and roadside development in urban areas also makes drivers adopt a lower speed than design speed in some hours during the day, which calls for using lesser superelevation rates. These are another reason for establishing different maximum superelevation rates instead of a single rate, and also highlights the role that topography and area type play in picking the right maximum superelevation. Presence of ice or snow on the surface of roadway makes drivers more cautious. They normally adopt speeds well below the design speed, so to minimize vehicles sliding across the curve, climate could restrict the maximum superelevation, which is another reason for establishing different maximum superelevation rates. All right, so far I tried to explain why different maximum superelevation is required instead of a single rate, and what's the difference between them. Knowing these informations help us to get a better understanding of their applications. So it's time to move on to the second question, which maximum superelevation rate we should use for a specific road. In rural areas, when snow and ice are factors, or heavy vehicles operate at a speed well below passenger cars, or when horizontal curves are combined with steep grades normally equal or steeper than 4%, maximum superelevation of 8% is appropriate. Regardless of the mentioned conditions, generally 8% is considered to be a reasonable maximum superelevation rate for rural facilities because it provides a reasonable proportion of side friction and reserve adequate for rural areas. It's common practice for highways and freeways in rural areas to be designed for a maximum superelevation rate of 10%, sometimes even up to 12%. But notice, given wide roadways associated with highways and freeways, sometimes using these rates may cause problems. For instance, using high superelevation rates may makes it difficult to provide enough height for culverts unless we increase the embankment height, which costs more and it's also not desirable safety-wise. So there are situations selecting 8% as maximum superelevation rate becomes more appropriate even for designing highways and freeways. In urban area where we're dealing with more constraints like drainage and adjacent land use, 4 or 6% is an appropriate maximum rate for high-speed urban facilities. These rates, as we discussed, reserve less proportion of side friction, but since due to roadside development and also congestion, drivers operating at lower speed compared to rural areas, this narrower margin of safety is still acceptable in urban areas. All right, I think it's done. Let's finish this video with two more important points. First, once a maximum superelevation rate is being selected, we should keep it within a region of similar climate, area type, and topography. Otherwise, the uniformity of the highway alignment will be affected negatively. And second, none of these maximum rates are applicable to low-speed streets in urban areas and also some turning roadways. It's a whole nother approach we'll discuss later in the following videos. Thanks for watching. I hope it was helpful. I say goodbye for now.